If u and v are real functions which are harmonic functions in a domain, then the function v is said to be a harmonic conjugate of the function u if the Cauchy-Riemann equations are satisfied. We have one theorem which is rather important. It states the following. If we have a function, complex function f of z, which is equal to u plus ev, where u and v are real functions, and this function is analytic in a domain if and only if the function v is the harmonic conjugate of u. Let's take this task. Find the harmonic conjugate v of the function u given by y in the power of 3 minus 3x square y. What we always do in such cases is that we take first and find the first order partial derivatives of this function u in the x and y direction. And it's rather easy to do this. We take the partial derivative of this with respect to x is of course 0, because the y is a constant in the x direction. So we easily find that the partial derivative of u with respect to x is minus 6xy. And we also find the partial derivative with respect to y easily. Next, we use the Cauchy-Riemann equation, the first Cauchy-Riemann equation, which states that ux is equal to vy. Ux we already have here, this value, and we just inserted it, substitute it, and so we know that the derivative of v with respect to y is equal to this. By integrating, we get the value of v. So integrating this part with respect to y, we find that the integral the antiderivative is equal to 3xy square. It's rather easy to see this just by differentiating. And we must have some constant with respect to y also, which we add to this. But this constant is only constant with respect to y. It's not constant with respect to x, so this must be a function of x. Okay. Next, we take the derivative of this function with respect to x and use the second Cauchy-Riemann equation, which states that y is equal to minus vx. So when we are taking the derivative of this expression with respect to x, and insert this instead, or substitute this part with this expression. On the left hand side, we insert the value, the function of u with y here, which we have found earlier up here. Then we are able to compute the value of k, the derivative of k of x. So you see here we have 3y square on both sides, which we can eliminate, and we find that the derivative of k is equal to 3x x square, which means that k must be equal to x to the power of 3 plus some additional additive constant. So what we have found here is this value of k here. We have found the expression for this function, and therefore we know what the function v is equal to. So we can insert this into this expression. So let's do this. We obtain finally that v is equal to this. Let's now turn to some exam task many years ago. We have a function u, which is the sine hyperbolicus to x multiplied with the cosine of y, and well, it's this formula were given. These formulas were given, so we can find the derivative of sine hyperbolicus and cosine hyperbolicus, and we want to show that this function u, firstly we want to show that u is an harmonic function. So what we are doing is to find the derivative of u with respect to x and the derivative of u with respect to y. So this is rather easy, and doing this once more we find these two expressions, and it's really trivial to see that the sum of these two expressions are 0, which proves that u is an harmonic function. Next we want to find an harmonic conjugate of the function u, and we do similarly as we did above. We use the first Cauchy-Riemann equation. We already know that the derivative of u with respect to x is equal to this, and using this first Cauchy-Riemann equation and integrate to both sides, we find this expression, and again we are using the constant here, which is a constant with respect to y, but it's not a constant with respect to x. And taking the derivative of v, that means taking the derivative of the left side of this equation, we find this expression. And now using the second Cauchy-Riemann equation, and note that we already has the expression for derivative of u with respect to y up here. Let me show you. We have it here. So therefore we can use this second Cauchy-Riemann equation to find to now insert the derivative here of vx, and next find the function description for k derivative with respect to x. So this is equal to 0, so therefore k of x must be a constant. And then we know from this expression that v is equal to this plus some constant k.